So this is the final paper talk of SGP 2026. The paper is entitled MM-CAD. I'm not sure if it's pronounced that way, but I'm going to pronounce it that way. A multi-modal CAD dataset and benchmark for cross-modal geometric learning by Bharathi, Aravindakshan, Muthuganapathy, and Bharathi will be giving the talk.
Yeah, good afternoon, everyone. I know this is the last talk, and you're probably exhausted. So I've kept a lot of visual intuitions. So hope you find it. So a brief history of shape datasets. In the beginning, there was nothing, and then boom came the generic shape datasets, ModelNet, ShapeNet, PSP, Thingy10K. These were the standard datasets that people use, but these were more organic, and they would relate to the practical shapes that you see in real life, like chairs or headphones, whatnot. And then there were engineering benchmarks, which were focusing on CAD models that were produced by industries, and here the focus was more on trying to capture the engineering intuition behind models. And there were also other types of dataset like the Fusion 360 dataset and the Sketchcraft dataset, which were more aligned to the parametric side of things. And then came the ABC dataset, which had 1 million models, which were very diverse and covered almost every type of domain that there is. Even datasets like ModelNet were having similar models because people would try to create 3D printing objects like sculptures and whatnot. So there was a lot of diversity in this data set, and sadly, it was not completely being used to its full extent because the sheer volume of it. There is 1 million models, and it includes everything from assemblies to individual parts and complex shapes. So, and currently in the landscape of CAD-related models, they all focus on one objective, which is generation. They've tried different tokenization techniques. They've tried different ways in which you could generate CAD models, ranging from fine-tuning LLMs to diffusion models to having custom architectures that will provide CAD operation sequences. But if we try to ask what the industry really needs, how is the typical workflow of engineering in an engineering design environment? Engineers usually retrieve CAD models more than creating a CAD model from scratch. Most of the time, a normal engineer would try to find it from a pre-existing database like GrabCAD, or they'd have these descriptions of the CAD models where it's like usually indexed with the particular terms. And these terms must be very grounded, and they're very dense. Like you might have cylindrical bosses and herringbone gears, which are not completely understood by the existing data sets, because the generation models are a lossy compression of the entire data set. So, and consumer, and one other application domain is, another interesting application domain is in jewelry retrieval, where companies have these large CAD databases which have these diverse shapes, but the user queries is more like hand-drawn sketches or like real-life images. So there is a requirement in industry for such modalities, such understanding, geometric understanding from modalities. And generative models are a lossy compression, and obviously they would if you're importing a model in your GPU, you'd be spending VRAM for jewelry models and aviation parts. You'll be the generative model would have to compress all this geometry down into your VRAM, which is not necessary for a person working in Boeing. They don't need jewelry datasets. So there is a requirement for a multimodal CAD retrieval engine which has really deep feature understanding, which is what we're trying to address over here. So we tried doing this by having two versions in our data set, which was MM-CAD A and B. A was more of the hand-tuned data set where like we manually sampled 33,000 CAD models from 11 different shape benchmarks. And we almost manually annotated them with text and hand-drawn sketch captions. And we used this data to train models that would either be used for sampling models from the ABC dataset or be used for annotating the models from ABC dataset. I'll get into each of this in detail now. So how did we curate MM-CAD A? We first sampled 33,000 CAD models from 11 datasets. But this 11 datasets is a bit of a stretch because most of our, like almost half of our dataset was from MCB dataset. And we were able to sample easily from them because the CAD models were easily categorized. And we almost half of our dataset was from that. But for the remaining datasets, we just sat through the seeing every single CAD model through a grid, and like we selectively chose the ones which were resembling more of what it would fit in an ABC distribution. And then we had, obviously, the geometric modalities of the point clouds, which were sampled through Monte Carlo sampling, and we made 2D renders. And then for text captions, we made drafts with GPT-4, and we gave it to 10 engineering design students. And we instructed them to take 2 to 3 minutes per CAD model. And they would try to see where the model is hallucinating, where it made mistakes, where it could not be verified. And but when we scale it up to 33,000 models, almost every person whom we gave the annotation work to was having increased rates of failure, or the structure would not be all there. So we had to keep another layer of Gemini 2.5 Flash model to review the captions. And then we had Sketch, for which we sampled, again, 1,100 models from all the different benchmarks, and then we told annotators to sketch, to actually trace the render. So we have two different types of sketches. One is the trace sketches and the hand-drawn sketches. Hand-drawn sketches would be something like you look from the render and you trace it up in your iPad. But trace sketches would be, you'll have the render and you'll be sketching on top of it. So we use this to train our models, and we used this train model to generalize over the entire data set. But this operates purely on the image modality. So to sum it up, we have about 4.3K real engineered drawn sketches for CAD models, which is the largest there is for CAD models. And then we have 33.8K manually annotated text captions for CAD dataset. Overall, this pipeline took us about 1.5 years, and it was very rigorous. And now comes MM-CAD B, where so we use this data set to train a point cloud encoder and to give us multimodal aligned feature vectors. And I'll walk you through the process over here. So from the entire 1 million models, we first pre-sorted it just based on the renders so that we could make it life a bit easier. And sorting was done through an image model, but I think I don't have time to explain all of that in full detail. But yeah, the pre-sorted list was deduplicated, and we had about 687K distinct CAD models, and we split it into 100 chunks, and we encoded them into vectors, and we clustered this, and we sampled adaptively from this, such that I'll get to it. Yeah. So when we clustered it, we found about 114K clusters for the 687K CAD models, but the Gini coefficient was 0.3. And the mean cluster size was 2, which means that we had a very large tail of CAD models, which also made sense because a large amount of CAD models were unique and would be hard to classify them into separate classes. But then there were some CAD models which are very similar, something like nuts or bolts, which would repeat so many times in the data set, or which has so many different variations that even if you deduplicate it, there is a large amount of them. So the idea was that we take an even sampling, and we have some heuristics-based methods to do that. But finally, we have all these modalities. We have point clouds, we have renders, and we have feature grounded captions, and we have photorealistic images and hand-drawn sketches, and all of this organized into a neat taxonomy, which I'll get into each modality now. So one thing that people didn't notice, in the current landscape, the CAD text descriptions was given through making a large VLM see the image of the CAD model and just make it describe it. But we also had these feature trees that was used to construct the CAD model, which had much deeper details about how it was done. And I don't know if you're able to read this, but it has what part this is supposed to be. Is it an arm linkage or a leg linkage? So we parsed it, and so this metadata was openly available along with the ABC dataset, and we parsed it up and we fed it to an LLM, and such that we have this kind of context to this LLM. And the same LLM was given the two renders of the CAD model, and it was given a system prompt. And the final captions that we had was very grounded in the reality of the CAD model. So the same VLM, if we gave it without this construction context, was able to give better grounding, better alignment to the ground truth in all of these features. And as you can see, all the basic details were captured properly by the VLM alone, but the much more detailed and specific queries, which would probably be the thing that's necessary for training a high practical engineering design model, were missed in the existing methods. So that is about text. And for photo renders, so we took these 2D CAD renders and we passed it through Flux to a diffusion-based image generator. And since we also had this kind of context details, which is like what is the particular application this is supposed to be there for, and we used all of this detail. And sometimes the individual parts had the material details. So we used all of this and fed to another LLM, and it gave guidance prompts to the image generator LLM. And as you can see, we're able to get relatively geometrically grounded and material aware sorts of photorealistic renders. And the sketches, we reuse the same technique that we used for MM-CAD A, where we already trained it with the sketch generation model from the manual sketches, and we used it to generalize over this data set. And this is the reason why I said that we sampled it very, very particularly so that it matches ABC's distribution. So what if we want application-level classes? So in MCB dataset, it was categorized neatly into what kind of application category this would belong to. So let's say if I were to only work on robotics domain, I would only care about the CAD models in this domain, right? So we tried classifying the CAD models into their application categories. And this we were able to do because, again, the metadata was available and the LLM was instructed the text caption generating LLM was instructed to give us the application keywords that this CAD model would potentially belong to. And as you can see, we're able to get a really nice looking tree. And the way we did this through a process called Dirichlet process Gaussian mixture model, which sounds like a lot, but the idea is that instead of a normal k-means, KNN clustering method, we use this technique to adaptively identify how many branches that they would exist. Because as you can see, if you use a k-means or a fixed clustering method over here, we wouldn't get these kinds of rich branches of where each and every component would belong to. So, And this can be inferred from the data alone. So what we did was we encoded the application keywords through another text embedding model, and the idea is that these kinds of shapes these kinds of applications would align as Gaussians in the latent space of the text embedder, and we would recursively break down these Gaussians into the particular application categories. So we also evaluated this data set because it's completely synthetic, but we evaluated this by sampling around 750 models across the entire data set, and we made annotators rate how much the material was realistic, how much was the geometric fidelity, like how well the images captured the geometry. And similarly, we had similarly, we had done it for sketches, and we had done it for text captions as well. And with text, we compared it with the pre-existing CAD datasets. And as you can see, we're able to get a good performance leap through all these techniques that we had. So to benchmark this, we had trained 5 encoders with this data set. In the first stage, we trained text, brep, and point cloud together into a symmetric info NCE loss, and we tried to get this geometry native latent space. And then, since we want this multiple modalities, we used a sketch encoder we used a VIT encoder for sketches and SIGLIP encoder for images. And first, this was trained together to give the. Okay, yeah, I'll get to the next slide. Yeah, so this might look intimidating, but basically here we had evaluated it across different modalities where text and brep was evaluated, and sketch and brep was evaluated, and text and point cloud was evaluated. And what really has to be focused on over here is the joint retrieval, which was for text to CAD retrieval, native text to brep retrieval. We got 15% recall at 1, and when we combined all these modalities together, we got 45% of the retrievals were correct, and I'll show it qualitatively. So yeah, this is an example where we combined all the modalities. Since all of them share the same latent space, you could technically combine a sketch along with a real-life image, or a sketch pad with the text description. And this actually improved the performance because there are lots of details that people can't represent completely through sketches alone, and some details cannot be represented through text alone. So we were able to find this complementarity in this data set. But this is not completely feature-grounded as well, because this also has failure cases where something very specific, like a herringbone gear, which has these kinds of V-shaped teeth, these were not learned properly by the model. And similarly with V-groove pulleys. So these particular application scenarios, this model failed. So what did we do to fix it? So I'm going on a tangent here, but in text, there is something called as byte pair encoding that was done to identify these distinct tokens from a large corpus based upon how these characters would co-occur across the entire corpus. So we thought, what if we could try something similar for CAD or geometry? What if we could see if similar types of faces would recur across the entire data set, like a teeth or a blade or a counterbore? So these features would be repeated across the entire data set. So we thought, what if we could try to find a way to tokenize that? And we did find some relative success with it, but it's not completely there, which is why we leave it as an open problem. So as you can see over here, it is not doing it completely for all the different teeths, but it is able to find these slanted teeth properly, and it is able to identify them as separate units. And so the same applies to this impeller, where the blades are getting categorized properly. And this is within part. Across parts, we are able to see that the through holes that was there in all these different models were given the same token ID. So from the experiments, we found out that almost 65% of the faces could be tokenized, and we were able to get this kind of neat decomposition of the CAD models. But this is basically a type of compression that we're trying to do, and there is always going to be a residual part which is going to be unique for every CAD model. So if we just see the vocabulary like this, we get about 120K prototypes. But yeah, but okay, I'll get into this. So how we did it? We took the BREP as a face adjacency graph, and we were basically trying to identify these subgraphs which we could call as geometric units or motifs or whatever. But and these subgraphs we would hash them with Weisfeiler Lehman labels or with geometric descriptors, and we would try to because of the compute requirements, compute limitations we had, we started with a lower number of features, and we iteratively grew the graphs such that it would start with only 2 faces, and then it would iteratively grow up to 32 different faces. And we found out that this doesn't decompose entirely well, because as you can see, this is more like a face level decomposition. But what we really want is what we really expect from such a tokenization would be a geometry level tokenization, a volume type. So we thought that we just leave it as an open problem based on whatever we identified, that these recurring units could be compared based upon the chamfer distance, and we could keep some amount of tolerance between the different units, and the boundaries could be boundaries of these faces could be kept not based upon purely the dihedral angles alone, but based upon the volume addition and removal. I know I'm rushing through a lot, but time limitation. But yeah. Qualitatively, this is how, after the paper, we even tried this chamfer congruence, and beyond the faces, we tried this ourselves, and we were able to find a relative amount of success, and it was able to find these teeths properly in gears, and it was able to even find the slots, but it was not consistent across the entire CAD model. And one other thing that we did was, since we had these rich descriptive text descriptions, we took the keywords out of the text descriptions, and we saw how well these keywords correlated with these repetitive units. And we found that words like slot would co-occur a lot with this particular unit. So it would automatically categorize just from the BREP alone. And this could have applications in ground. This could be used to train models to have better grounding of the CAD models, like better semantic grounding, and yeah, or this could also be used as a quick decomposer. If you just input the CAD model, we automatically will be able to tokenize it, and this could be later used for generative applications as well. But we leave it as an open problem because we were not able to completely solve it. But yeah, that's it.
Great, thank you very much. Running a little short on time, but are there questions from the audience? Yes, please. A microphone, or you can take mine.
Thank you for the interesting presentation. On the slide number 16, the quantitative evaluation of the photorealism was mentioned. I might have missed it, but could you please expand a bit on, let's say, for instance, material realism or other metrics there?
Yeah, so that's a nice question. Material realism was like we instructed the annotators to say if in a practical application of this CAD model, would this material be realistic? Because frankly, the metadata would not always contain the exact material that was used for the CAD model. So we were trying to identify since we pass it through an LLM layer, the LLM would try to categorize it based upon the application that it was trying to use. So we were trying to see if this LLM part captures the variance properly. And same goes with the geometric fidelity, where we're really measuring the image generator, if it's able to follow the target geometry properly. And the camera angle and background were other parameters that was there given to the image generator as a part of the, and we were basically trying to see if these would be a realistic sort of, if you really had this CAD model in front of you, and if you took a photo of it, would it involve these camera angle? Would this camera angle be right, and would it be in this background? That's what we were trying to capture in photorealistic.
Thank you.
Thank you very much. Let's thank our speaker and I don't know if our remote speaker can hear us, but at least in spirit, let's thank all the speakers in this session.